I'm going to walk you through in the next hour what I would describe as a fire hose. I think you're familiar with fire hoses after the past several days, but a fire hose of ideas about scientific codes. And I'm going to do that to feed you some ideas to think about for the talks in the next couple days. So you can ask the speakers, as very targeted questions, and maybe even divert them from what they're talking about then, but to sort of pull from them as much as possible, because the speakers for the next couple days are all applications people. They're all people who have spent their time thinking about, how do I write a really complicated scientific code? And really, that's the theme for this talk, which is that scientific codes are complex. They're addressable and they're writable, and you can attack this problem without a doubt, because people do it all the time. But no matter what, they're complex. And if you want to think about everything that goes into them and all the things you need to worry about globally, they're complex. So that's it. There we go. All right, I'll have to hit harder. And so that's really this theme. Now I'll caveat. I stole this picture mostly as sort of a fun illustration of one of the ways that people have conceptualized scientific applications. This is from a productivity workshop about how you can be productive writing scientific codes, which is a loaded idea. How can you be more productive writing scientific codes and do them faster and better and easier and all of these things, and cheaper, and all of these things are in conflict. But it really gets the right ideas across, right? So that when you're writing scientific code, it's not just that you go off and you write some code and you run your problem and you're done. It's a complicated problem of figuring out what type of problem you want to do, what methods, what applied math you want to use, writing some code, iterating with that to figure out what the problems are and debugging it, getting some results, doing some analysis, maybe rewriting some code. And it never really stops. It's a continuous cycle of developing and iterating. Well, I should say it really rarely stops. And if the code, my statement will be that if your code has any longevity, it really doesn't stop. Because if you're really pushing the code very hard, it will need to adapt, it will need to incorporate new physics. And on the left, I just list, right, these are some of the general things, right, that people think about when they're putting together scientific code. I mean, without a doubt, and I don't ever mean to trivialize this in this talk, right, the absolutely most important thing is whatever your science or engineering is. And so even if I diverge from that, keep that in mind, right? I'm not trying to minimize it, because you can't design a code unless you have a problem in mind. And I feel very strongly about that. But we've talked about throughout the program a lot of these ideas. And I think I am going to infer, and sort of having looked at some of the material because I missed the first week, that really the verification and the validation have been implied by some of the conversations, some of the talks that have been come around. But I'm going to talk more about that today as a very concrete, real part of the flow for designing and creating or using a scientific code. And then the concepts of scientific engineering. And so as we go to the next couple days, we're going to have some conversations about software engineering principles tomorrow. And no matter what level of code you're writing, some of these things are directly applicable. And I will certainly express my opinion strongly about those in the next hour. The other thing I'll say about the next hour, and I mean that, and this will apply to the whole day, I hope too, is that I'm about to talk about one of the fuzziest things we're going to talk about the whole program, because there's no single answer. Even if you are working on a turbulence problem and the person next to you is working on a turbulence problem, unless you're looking at the exact same turbulence problem, different things here might be important to you. So ask questions. This particular intro, as I said, is a little bit general, but ask and drive and sort of help. It will help, I think, you in identifying maybe what you really particularly want to worry about, but we can also share our experience with it. I can say that the people coming in have had cumulatively many years of writing codes, and there's some really good brains to pick. All right. So not to be too trivial about it, right, or at least too comic about it, right, that mostly the tracks since the start of the program have covered what I would argue are the big sort of starter things you have to worry about when you're writing scientific code, right, that aren't your problem. Like you're talking about the architecture. Well, you can't really write a code, ideally today, and this will come back, without having some sense of what kind of computer you're using. You need to know what kind of methods you're using, right? You need to understand how you're going from your equation to a code, so you need to understand the applied math. And very, very direct things like, how do you do I/O? But also not only how do you do I/O once you have all of your data, how do you think about that? How do you manage it? How do you move it? And so theoretically, right, you could just take all of these different parts and plug them together, and you get a code. And while I really don't mean that to be trivial, right, trivializing the problem, I would say that for a while people sort of thought that way. That I can just take these things, throw them together, I can do it on my own, I can have sort of this hero effort, and I can just get my work done. And I think that is becoming far more complex and far harder to do. So one of the other things that I'm going to feed into today, I don't resort to cutesy pictures and talks very often. But what I wanted to talk a little bit about was that everybody's trying to do this, right? Almost everybody, which is to get some science or engineering out. And to do that well in scientific computing, you really need to feed that with a scientific process, which has sometimes been missing from computational science. And you need to infuse into that scientific process and into your science also a software engineering practice. This doesn't necessarily have to mean the scientific, the software engineering practice of somebody at a bank writing code, but there are some practices you need to incorporate. And historically, all three of these things haven't gotten along really well. And it's not because they're not trying to get to the same point, right? There's, I would argue, not a whole heck of a lot in software practices that is going to make you cry, right? Or is counter to the process of getting out good science. It's just that they haven't gotten along. And there's been a lot of different reasons for it. One of the reasons is a little bit sociological. If you are a domain scientist, in almost every domain, and you're trying to get out publications, you might not get rewarded in your university for worrying about the software practices and the scientific process. You might not. And over the course of the past, certainly 30 years, you haven't always had a place to go to publish things like a documentation about the code, right? If you look at an experimental apparatus, most experimentalists actually put out a paper that says, this is the apparatus that I am using, right? And people get credited for that, and you get citations, and that paper is valued, right? And so there have been long historical, and I'm not claiming it's resolved, but certainly it's been worse, problems with publishing that paper, that experimental paper. This is my code. This is my experimental apparatus. That maybe doesn't have to be a full paper, but you need to document it. And so these things are getting friendlier, right? All of these concepts are getting friendlier. They're crucial to putting together a scientific code well, a scientific code that you can trust the results to, and a scientific code that I think really will have a future going forward over the next several years. And so, as I say here, I think it's really that they're getting friendlier in part because they have to. I think there's been a lot of push by the community to say that if you want young scientists to worry about the scientific process and their code, then you need to reward that somehow, right? You need to have a mechanism to actually have that contribute to their future and their career path. And also, as has come up over and over and again, that these problems are getting more complex. So, as many of these processes are making peace. The other side note I will make as we go forward is that I worried when I sort of put this together to sort of fire hose you with a whole bunch of ideas about what goes into a complex scientific code, that it would come across really, really hard. And I'll talk a little bit about that, but it will sound like just this litany of things you have to worry about, otherwise it'll be a disaster. But it's mostly I want you to hear about these ideas so that you can figure out what will work for you. So it's sort of, again, sort of this concept of a list, but on the left, right, these are all of these ideas that have been discussed, very concrete things like libraries and methods and architectures that have been spoken about for the past few days. And those all apply to sort of larger larger concepts in doing computational science, right? So besides the practice and the process, right, portability, performance, resilience, right? So in the end, right, Jack's talk was sort of this perfect transition talk about talking about really hardcore performance and algorithms, but how that impacts larger things. And he was talking about resilience. So does your code, resilience can apply to a lot of things, including, if nodes fall and you're running a 1 million core simulation, what do you do? But also, even resilience in how you develop it, right? How resilient that code will be to changes in architecture. So these are a huge suite of concepts, and I'll poke at a little bit of these. And they apply so heavily because really what you're going to experience is that no matter what you think, your code will live longer than you think it will. I mean, it will. Somebody will find it. Even if you think this is like the thing you're just writing and throwing away, unless you hit delete on something that's never been archived, somebody will find it and pull it out and go, oh, well, that's interesting, right? And and come back to you 5 years later and go, hey, what did you do when you wrote this? This is interesting. Can I use it? That's kind of extreme, I realize, but they do. This code lives longer. You prototype something and you experiment with it and you end up sort of keep on building across something that you've prototyped. So some of these ideas are really useful to think about from the beginning. So this is it's sort of an eye chart in many respects, and it's mostly to illustrate an idea. I don't fully agree with every single arrow. And so what this gives is a sense of, this came directly from a book by Steve McConnell called Code Complete. It's sort of an interesting book, and if you're interested in sort of writing and exploring the world of writing code, there's a lot of interesting ideas in it. But what he wanted to address was sort of to give people an idea. If you look about writing code that's correct, right? That gives the correct answer, but that's also usable. So you don't have to go and spend 6 months figuring out how to use it. That's performant, right? That's efficient. That has, that's adaptable, right? So you can easily change it to bring in a new problem or go into a new architecture. I wanted to give a sense of the relationship between them, right? So if you write correct code, how does that impact all of the other things going along on the right, okay? And so clearly if you write correct code, that has a positive impact on correctness. And so that's the one thing, there's always a positive impact along the diagonal here. But these are all primary things you might want to think about when you're writing code. And whether or not we quibble about one particular direction of an arrow, and I have at times quibbled about some of the directions, because this is a little bit old at this point, it shows that there's a very complicated set of trade-offs you need to worry about when you're writing code, right? That just because you decide you're going to write the most usable code, you have to understand that you're going to be making some trade-offs. And so, and they're relatively complicated. So what I have no issues with is that it's a complicated, sort of messy picture of the relationship between all aspects of codes. And that's why I would encourage people to think very carefully about the choices that they make. There's room for error, and this goes back to the thing, I don't want to sound too ominous, right? But you have to think carefully. Okay. So as I said, this goes back to the fire hose. I'm sort of switching slightly to sort of this concept of what I mean by the scientific process with scientific computing. And I'm sort of curious how different this sounds to people. I know that this wasn't as universally accepted, I would even say 10 years ago. I think a lot of people saw the need for it, but doing it was often pretty challenging. So what is the scientific process here? It's really having code that gives you answers that you trust, and that's sort of the end story of it. And it's important. There's actually a really cool paper, cool not if you were the scientist who ran into the problem, but a really cool paper in Science from 2006 about the sequence of retractions that this crystallographer had to do because he used a data analysis tool that his team had developed, but there were pretty significant errors in it. And so he had gone forth and used the tool, hadn't really sort of attacked what the tool was doing, and had some pretty significant errors that were caught post-publication. So it was a series of 5 retractions from Science, that happened as a result of that, and that's not a low profile retraction to have. And one could argue, right, that this really was his fault, right? If you're going to use a code, you have to understand what that code is doing. And does that mean you have to go and rewrite every line of code to understand what it's doing? Not necessarily, but you have to understand what abstractions it's using. You have to understand what methods it's using and how it's doing it. And you have to check. So this is not even if you're writing your own code, I would argue, even adopting codes that already exist. So what are some of these things? So one of them is error bars. Jack also spoke about this, and it was a fantastic lead-in, right? Because people often don't, you look at scientific papers, very few of them have, scientific computing papers, very few of them have error bars. There's real error here. There's real error. You are making an abstraction from your equation, right? To get your applied math so you can write your code. And there's error, and that's well understood too in many cases. in many cases. So if nothing else, there's already error that exists in these things, and assuming that sort of people are considering that, I would say is an incorrect assumption. You have included in that you have numerical sensitivity tightly coupled to the error actually within the algorithm you're using. Machine rounding, right? This is a little bit more controllable is the wrong word, but in some regard maybe is a little less pervasive, but it's still a source of error, and you need to understand how that percolates. Going back to sensitivity, right? Some algorithms are really sensitive to that. And there's been a lot of effort in this sort of general area too with uncertainty quantification in the past few years. And that's one of the things uncertainty quantification is trying to get, right? What are the error bars on these? How sensitive are these algorithms in a few different dimensions? Verification is another part of sort of the software engineering process where you really want to think about if your code is doing what you think it's doing. That's the short version of what verification is. There's good techniques that people have for this, but you want to make sure that if you wrote a subroutine, it keeps giving you the answer you expect it to give. And you want to make sure that your code is actually giving you reproducible results, and there isn't something in there that is unstable. Validation is a much more complex one. That's much more closely tied to your area of study. I think it's one that has actually been better addressed over the course of scientific computing. So a lot more people have historically taken their codes, tried to compare them, say, with experiment to actually prove that your models capture the physics of what you're interested in, right? You want to prove that your models are right. And then this very larger thing about reproducibility of results. And this is a big beast. It has several heads, right? You want to make sure somebody else can reproduce your results. This again goes back to, while I don't believe the experimental world is perfect, right? They have a good history of this, right? Somebody claims they've solved the problem of cold fusion. You immediately have 3,000 scientists going off and trying to reproduce their experiment to see if they actually did solve the problem of cold fusion. So you want to make sure that if you publish some results, that if there was somebody who wanted to try to reproduce your results, they can, right? And that includes understanding and documenting the code you used, the version of the code you used. This is not like hours and days and days and days of effort, right? But if you just take a stamp and a tar ball of the code you use to preserve that attached to the data that you generate to do that, that's one very straightforward step for that. Data availability is one of the other ones, right? That comes up quite a bit. So providing your data so that people can analyze it and poke at it themselves. So this is just a slight iteration of the same slide, but with some of the things I've already talked about ways you can actually attack these problems. And one of the ways that I think is a great illustration that the community is moving forward with this idea about people being able to look at data and do their own analysis on it and see what they can figure out is Science has a new subjournal, Scientific Data, and they provide some criteria. It's peer-reviewed, so you've got to get accepted, but they provide some criteria for how they want you to describe their data, and they actually will be providing data for people to do analysis on, along with accompanying paper and documentation associated with it, right? And I forget exactly how long they're committing to keeping that data available, but that it's one of their new online journals, which I think is fantastic. It won't solve the problem of the entire world of scientific computing and all of the data that people are generating, but it's the start, right? And it's a pretty high-profile journal to start doing that, and that has impact, right? If it was a little tiny journal that only 2 people really cared about, that's very different than Science attacking this problem. All right. So this gets back to the transition to sort of make this point, right? That I'm not trying to drive people away by describing an incredibly complex problem in 5,000 things you need to do, when perhaps there's only 2 of you working on a code, or maybe 1, and you have limited time and other priorities to get along. So the most important thing is that you have some idea about what these concepts are. So when you start working on a code, if you are an individual, a single person working on a code, frankly today there's a limit on the complexity of that code, or at least how fast you can generate that. And I have previously in my time been able to generate code really quickly, but there's still a limit there. So there's very easy things you can do early on to make your life sane But as your code grows in complexity, and that includes scientific complexity, sort of engineering complexity, or even, sorry, I can't speak, sort of science complexity or architectural complexity, you need to worry about more of these things. And that will be sort of one of the unifying things in several of the talks today, which is sort of, these are all codes that have a large user base, that solve a large number of problems. So they're pretty complex codes. And so at some point, they've needed to address many of this litany of things that I'm throwing out there. And this is, again, I think, iterating of the bit you've heard many times, so I'm not going to belabor it too much, which is that if you are alone and you don't have many cycles to worry about everything I'm talking about, the first and most important and most relevant thing to worry about in writing a new code is really what your data structures are and where the parallelism in those data structures live. If you're writing a new code, that is the thing that is going to enable you for the next several years. And if you haven't thought about those things, something in the not very far future is going to end up kicking you back with a bat to say, go ahead and think about them, without a doubt. I promise you. And this is, this came up with what Jack was talking about, and I'm sure this came up in some of the other conversations last week. And one of the other aspects of thinking about your data structures, and I'm jumping ahead in slides, is because that also might impact or be impacted by what existing code bases you want to use. If you want to use libraries, it's really worth your while to say, well, Petsy thinks about its data this way. So if I write an entire other code that I want to plug into Petsy, you want to make sure you're not doing massive data transformations in order to use a library, right? And so that's sort of this other, it's a little bit more mechanical aspect to it, rather than globally thinking about this from an algorithmic perspective, right? Thinking about what your data structures need to look like. Okay. So I've talked about all of these parts a little bit already. And I want to talk, but I want to bring it back to sort of collect why the software process is important. I should have said that I've tried to credit most of the slides where they were relevant, where I've sort of either hijacked or sort of pseudo-hijacked from somebody else. And I don't know why this one didn't get it, but this is Anshu's slide. So modern scientific, so the premise is what I think I've said a couple times, right? That if you want to do modern, large-scale scientific computing, it really is not a solo effort. It is hard for the individual to go off and write a big code to run on the biggest machines all by themselves with really not using something from collaborators in some flavor, whether that's libraries or collaborating with writing code. So, and given on top of that, if you, again, this other idea that I'll go back to, sort of these productivity languages, which what that means are these languages that are meant to be slightly easier to use, faster to develop, that might help you, that are targeted to specific domains, or that are targeted to help you conceptualize your code a little bit easier, like even things like Chapel. Those haven't really delivered at very large scale yet. I mean, I'm hopeful that someday we will not be looking purely at the world of C and Fortran or C++ and Fortran, but we are right now, right? So that limits your speed. That also really does limit speed of development, right? You can write a code, probably as long as you know Chapel, you could probably write a code faster in Chapel, or you could probably write a code, certainly prototype a code a heck of a lot faster in MATLAB, right? But the scope of the problem you're going to do is much more limited. So this means that code does get complicated. It does mean you're writing things at a relatively low level, so it does take time, and it really isn't, as I said, this hero effort where you can go off and do something completely independent. At least, not with the final end game, say, of running, a really huge simulation on a very large system. Many codes get started on that individual basis, but in order to move forward, it gets much more complicated. And unless you have a scientific process, right, unless you have some rules and an understandable code, if you want somebody to collaborate with you on a code, it becomes very difficult. I have spent many, many, many months, probably I would say, of my life trying to eke out the essence of code where somebody just threw that together at some point or didn't document it. In some cases, actually, I know they were pretty well thought out, but they didn't document it, and they were pretty esoteric. It's that, that idea like with C of how many bits of functionality can you get in a single line. You can get a lot of functionality in a single line and you can't understand it unless you write it. And that's generally been true. So if you're trying to get, that can happen very quickly with code, right? So if you want to collaborate with people, having some practices, they don't have to be draconian. They don't have to be overbearing, right? They don't have to force you to write, beautiful, beautiful code, right? But if there are some practices that people can rely on, it allows them to read the code much more easily and collaborate with you much more easily. Bits of these will be spoken about tomorrow, but these are some practices that are really easy, for the most part, really not super hard, that people can start with. And tomorrow, Aaron Amadia is going to walk through some of these to give you just an idea about how to piece them together, right, and make sense out of them. But I cannot tell you how many people do not version control their code. And I see a lot of people sort of smirking, and that can either be that I'm finally talking to sort of, there's been enough of a phase shift that everybody's like, well, duh, why the hell are they not? But also, I imagine like that, yeah, I know, and I'm not. Because, just setting that up or like the infrastructure to do it, it can be annoying. But I really do feel like the universe for getting a version control on your code today is a hell of a lot easier than it was even 5 years ago, right? Even if you don't want to use GitHub, there are very easy to use tools out there that can help you track where your code is. And this will save you from a disaster if you haven't already had one. Chances are, chances are people might have already had disasters where something accidentally happens and you can't figure out when the last time you had a functioning code was. And this is one of the strong advantages of version control. It also allows you to be able to do something like just tag it. I ran this simulation on this exact version of the code. And that's very valuable, going back to this idea of reproducibility. You want to build process, so you have documented how you're building the code. That has an impact on your answers, right? Has an impact on what the code is actually doing. You want some basic set of code architecture and code standards, right? Again, this doesn't have to be, an incredibly complex, like working at Microsoft level of coding standards. They have very intense coding standards at Microsoft, for good or bad. But they need to be some, right? You need to document them so you have some rules about how you are putting your code together, right? And so that somebody else can read that later on, but I also promise you so that you can read it 8 months later. Again, this is all stuff you might have experienced already, but if it hasn't happened to you yet, I promise at some point you will go back to look at code you wrote and be like, I don't know what I was thinking. And the last two are, on the for all codes aspect, are I think very, well, I've already talked about verification processes, but they're ones to think very carefully about and don't necessarily have to be there as much on the first day, except that I'll say that verification, starting to think about verification from the day you write that first line of code, or the first time you take a code and you have to try to pull it apart, is the easiest way to do it, right? You write a subroutine, write 10 other lines of code that can grab that subroutine and just make sure it does what you think it does, right? And that's a lot easier than going back and having to write 100 of those unit tests at some later point. There are developing frameworks to help people do this, right? So help people manage how you would actually capture all those unit tests and run them and check their results without you manually doing bit by bit comparisons. But also, and so finally is also this issue of maintenance and support, right? The dominant way that almost all scientific codes get started is because someone's writing it in their lab to explore an idea or to solve a particular problem. And at some point, though, there is this transition where the code gets from, I'm experimenting, I'm trying to solve this particular little thing, it's not that important, to maybe this is a code that more than I will just use. And that if, that we might want to worry about how we're going to maintain it. And that does not mean, how do I support a suite of users that are external? But how will I document changes to the code, right? How, and this is relevant again to the scientific process, so and when answers might change and how they might change. Okay, so there's a lot of different flavors of codes. I think people have some sense of these. So that includes the black box, just grab a code and you run it. A lot of, there's a lot of examples of this, even at really reasonably large scale, of people who are just grabbing codes and running. My one comment here I'll say is, even at black box, people are responsible for understanding what they're running, right, and how it's running. But then it goes from, black box, where you're really not writing much code at all except for setting up the parameters, to altering existing codes, using frameworks, libraries that already exist, and maybe trying to piece your code together with that, to development of brand new code, like from scratch, you're just writing everything. There's sort of an overlap. These are not exclusive, right? You might be developing a new code, and you intend to use 5 or 6 different libraries in order to accelerate you along the path. But these are sort of the categories of development. And you'll see some of this with some of the codes we'll be talking about, because some of these codes are sort of built so that people really are sort of working on the alteration of, altering or collaborating with the developers to write a new code. But with that complexity, right, comes having to think about all these other things about software engineering and process that I was referring to, right? That you need to have a good grasp, say, on your development techniques, if you're going to have people starting to grab code and contribute modules, contribute physics, contribute capabilities. Okay, so this is another slide. This isn't actually a munging of a slide that a really cool code architect, is very, very good code architect from Sandia, put together, but I've simplified it. His was very targeted to a specific problem, a specific, I should say, framework. But I've always liked the way it captured sort of the components of what goes into any code. Doesn't matter how big it is, any code. It's just that some of these boxes might be really small, which is that you start really just with fundamentally what your problem is, right? Your scientific problem is, and the code that defines that. You start talking about then what the data will look like and how different parts of the code will use that, right? So if you've got a multi-physics code, how all of that data will move into those different components, and what that relationship is. And then you'll need aspects of the code if you're moving between different libraries or even different components of your code that need to look at the data differently. You need interpolations and data transformations. The blues are sort of all of these concepts of supporting your code, right? Where you need documentation, again, so you know what you did after you had a couple beers a few weeks ago. Testing your content, going back to verification, and this build content, right? So how are you actually compiling your code? And all of those things together sort of all piece into what really are the components of what any scientific code looks like. And they're all building on the set of tools, set of things on the bottom, right? Which are software engineering principles, so all of the productivity tools, frameworks and libraries, and this is just a typo because I mean this to be library. Library tools. And so but the libraries here really are referring to like solvers that you might be using with the larger frameworks, and the programming models and languages, right? So you can't really design any of these unless you've at least thought somewhat about what's going on the bottom, right? You need to know what programming model you're going to use to some degree, right? And the abstractions you might want to think about. Okay. So we talked about some just basic ideas of where to start, right? Where if you just think about your data structure and you think about your parallelization and how you're going to split those up, sort of just the first thing that you really need to worry about. There are other technical considerations too, right? Which are what you want to use to get to your problem, to solve your problem quickly. And this goes back to maybe not necessarily being a hero effort. There are fantastic tools out there, fantastic tools and libraries and frameworks so that you can build real scalable codes relatively quickly. But there are always considerations about those. And I'll discuss a couple of them, but one of them is sort of this concept of what ecosystem you think you might be working in. And it's the brutal truth that if you're going to target the real cutting edge type architectures, the ones that are coming out in the top 20, certainly the top 10 on the top 500 list, your ecosystem will be smaller than if you're using your university cluster, almost certainly. And so that means that if you're considering libraries and frameworks that are very complex, that have a lot of overhead, you're not as likely to find those, say, at leadership class facilities, or you might find them at NERSC, but not in heavy use, because there are overhead. People don't want to give over that performance, right? They don't want a code that'll run 50% slower. And so this is why people write their code in C and Fortran and use libraries like PETC and LAPACK, frankly, and ScalaPack, and the BLAS implementations that are really meant for large scale, but that's a pretty skinny ecosystem of tools and libraries. So you just have to think about what ecosystem you're targeting. But you can also think about this and abstract your code. Mostly this will mean data, but this also means functionality, so that if you change your mind, right? If you know right now you're targeting your university's cluster with a certain infrastructure of code, you can write good code that will be extensible, and where you can swap in scalable libraries later on that might be a little bit more complicated to use, but now it's really fast to use this other thing that's sitting there. Yeah?
One of the biggest challenges I've encountered in developing code is I'll be prototyping an idea. I'll be like, okay, how do I want my algorithm to work? Oh, here's somebody I want to use this technique, that technique. Here's someone who's provided a library for this technique in my prototyping language and that technique. Cool, I've got a great new idea put together, All right, now I want to make this, something that can be deployed on a cluster. Right. I need to convert it into a language that's, faster or whatever. And all these great things people have developed in my prototyping language, they're just not there. They're just gone.
Yep.
And so I say, well, what am I supposed to do now? Go and write this library myself in this language? And that's often, I've had projects that have basically stopped at that point because of the sheer amount of overhead in figuring out how to reproduce those libraries in a larger scale context.
The only thing I can say, to be completely honest with you, is you're right. You're absolutely right. This happens, right? The prototyping is there, and their tools are there because they allow you to very quickly test an idea and prove an idea to some degree, right? In limited scale. But many of these ideas many of the abstractions and the libraries and those higher level tools have, for various reasons, not taken off with the kind of performance that they need to be on, or to have the demand for these very large scale systems. And I corrected myself because partly it is demand. So, but it's very selective, right? It's this very incestuous demand, because you end up with users coming on these very large systems who want to have performance, and so they choose to write the code themselves, so they're not driving these problems, these software tools to be available on these systems, and then it's this vicious cycle, but it's been this cycle for like 20 years. But one of the other aspects I'll say to this is very often the developers of those tools that help you prototype, they don't get the funding to do a very complicated next step, right, which is to take a very high level concept of an algorithm and make that really performant on a very, very large scale. That takes investment. So the facilities, the leadership class facilities at the DOE, we try to deal with some of that, but we're never going to be doing something like taking these prototyping tools and turning them into scalable libraries, just because that problem is so huge. So really, in the end, what many people do in this workflow is they do exactly this first part: prove an idea and keep trying to sell it so that they can go to the next stage, right, which is get funding or get some time to do development. And without a doubt, get the paper out. I mean, I think a lot of people do it's a very valid step, right, both in terms of sort of validating the time you put into it, but also sometimes in getting the funding, right? So I don't have a great answer for you. It is true that the ecosystem on large-scale systems is really sparse compared to the larger ecosystem of HPC tools. Yeah?
This is the same kind of problem faced by experimentalists. You can do a small-scale study in your lab if you want to do a whole genome analysis or something.
That's a really
prove the concept, use that to get more funding, and then go and do the real problem you really want.
That's actually a really good point. I think about the experimental analogies all the time, but I hadn't thought about that. So I appreciate that. And this just goes back to this idea that this is one of the reasons I think that it's really a very collaborative field, large-scale computing particularly. Like the mid-scale computing, which are still thousands of cores, I think is getting more and more approachable because a lot more of these tools are available at sort of the university scale clusters. But when you start moving beyond that, you'll notice, as you have, right? And if anybody else hasn't, it's a drop-off pretty quickly. I even talk a tiny bit about this tomorrow, but I don't talk a lot because I think I've just told the whole story, right? But this is, so I'll just stop. Because but I will say, this is one of these reasons to, it's the strong impetus, I think, for collaborations. It's a strong impetus for code reuse. Library developers, for tools that do work on large-scale systems, the number of users that they have, and documented successes are real money for them, right? I mean, that is measures by which they're evaluated by their funding agency. So if you invest, say, in Petsy, I mean, this is not universal that just because you've invested in the time to use Petsy, say that means that Petsy will do what you want. But they have a vested interest in trying to keep you as a user and push you forward and perhaps, if it's something pretty extreme, finding funding to extend the functionality because they have enough users asking for it. But I mean, it's a real metric. They report, we have this many users, and these are the cool science that people have done using our library. And this is true across all the libraries and tools. So it's the one place where you can sort of indirectly feed into at least improving the capabilities of some of these libraries. I will say that this is also true about any code, too. If you pursue funding to write scientific codes, or you're trying to get funding for scientific codes, it all comes down to this. What were you able to accomplish with it, right? Do you have people using it? or and if you, even if you don't, right, if just you, what kind of cool things can the code do? And those are primary, pretty big metrics for understanding the impact that code could possibly have. For the sake of time, because I think some of this is been talked to a little bit, I will say one thing that there's been a historical, really improving mindset about not using code that already exists, like not using libraries, or not taking a community code, not collaborating with people and using a community code. There's been some pretty big obstacles. This is also one of Anshu's slides. I had the little Berkeley thing on all of them, and they seem to have disappeared. And so, or this might be Mike Rose, but so. Sounds like something I would say. Yeah. So there has been this reticence. I think in the past 5 years or so, we've seen a growth of more and more people trying to use existing frameworks. But globally, as scientists and engineers, there's a very understandable response that this is my work. This is the stuff that I need to get out, to move my career forward, and people want to own it, right? They want to understand exactly what's in it, line for line, and they find it easier to do that if they write the code from scratch. And they walk through the logic about that, thinking that, this isn't really exactly what I need. I'd need to sort of change my plan or change what I'm thinking about for my data in order to use it, so I'd have to munch things around a little bit. And sometimes those are very genuine concerns, but sometimes it's really, and this is the one point I really want to push on this, is that sometimes it's only maybe what you think you need. So if you're looking at something that you think almost could work, that is well supported, that you think has a future, so it's a tool worth investing in, but you're like, it's not quite right. Take a really close second look, because from a productivity perspective, which is at this point, productivity is sort of this buzzword that's sort of smacking me in the head a lot this past 2 weeks. It can really help you, though. It can really accelerate you along the way. But there are genuine concerns, right? The one thing I will say in terms of obstacles for code reuse that are real is you're making an investment in it. And they're going to try as much as they can to make sure that code, the developers, make sure that code persists. But this goes back to, interact with the code developer, the tool developer, so that they can persist. Because if they don't know of anybody using their code, chances are their funding model goes down very quickly. So, and I'm going to skip. This is a code. This is an idea. It's worth looking over. This is from this concept of, if you want to address the longevity of a scientific code, what are some concepts you want to infuse into the code so that even if you lose funding, the code has some help of moving forward. And they're interesting. I think they're valuable concepts to have in mind. It does not necessarily need to be ones that you're thinking about from the day you start writing your code, but they're ones that really help a code be easy for people to adopt. And people adopting your code is what keeps often a code around. So this is really the end sort of in terms of content. I sort of set forward this slide already earlier. Consider the ecosystem you're going to be using. Consider that, like, if you look at Argonne's leadership computing facility, if you look at what languages codes are written in, right? They're Fortran and C++. There's a little bit here of charm, and that's a real framework for writing codes, and it's a fantastic one. This is NAMD. For people who do not know, this is a molecular dynamics code that's very, very dominantly used to study molecular biology problems, but it is also C++ based. So, and the other two, which are Python, are really codes that are using Python as sort of an infrastructure, as an architectural thing. No code that goes and actually does compute is written in Python. So we hope, I think we were saying this 5 years ago, maybe 10 years ago too, that maybe this becomes a little bit more diverse. But fundamentally, for performance, we're still looking at, relatively low-level languages at the very, very large scale. And additionally, a lot of open source code, a lot of it. Most of the codes that are running on, so these are really, truly the Office of Science open facilities, right? So not what you see on an NSA system. Most of them are open. And this fuzzy category is because it really is fuzzy. They're not entirely open source. Like, you have to go sign a license and say, you're not going to go do anything bad with it, but you still get the source code, right? They're still relatively open source. It's just not what you would think of immediately if you heard of an open source code. Okay, so I encourage you to ask everything you can think of that might help you of the people in front of you. They've got a lot of experience. They've got particular things that they've put together for their talks, but really, I think I don't think anybody's shy about this, right? These people are here to help, right? Sort of give you advice about how on earth to move forward with a particular problem. So you'll probably get some diverse answers because they're all very different fields. So that's also sort of, I think, a pretty interesting way to attack this. And just remember that we're not trying to teach you the codes. I think for context, right, looking at the equations in some cases is very valuable just so you understand why they chose a particular data structure. But we're not trying to teach you, say, quantum Monte Carlo. We're trying to show you what a particular domain has done to try to solve this problem and to see if there's anything you can glean out of that. Okay. Any other questions? Yes?
Do you have any recommendations for how to pick up best practices when you're, when you're developing serial code, there's a lot of things that maybe don't apply here. So where do you pick up like those little tidbits other than just talking to other people?
There are a few good papers, very, very good papers. And actually, we can probably pull together a list pretty quickly. I think I had, I sort of have them sitting around at various points. These are, journal papers that talk about really good software practices for large-scale parallel codes, or even just parallel codes.